I'm Joseph DelPreto. I'm a PhD student here at the Distributed Robotics Lab, working with Daniela on human-robot collaboration. And the idea of this project is to make it easier for people and robots to work together as a team on physical tasks. And we're doing that by using your muscle signals as a way to communicate with the robot. So instead of having to explicitly tell the robot what you want it to do by programming, by speech, or by other means of communication, you can just use the muscle signals that you're naturally generating during the task. So this will hopefully make it easier to work with the robot as if you were working with another person. So by using this nonverbal communication, it makes it more intuitive to work with and almost like a natural extension of yourself. So by looking at my muscle signals while I'm doing the task and working with the robot can get a sense of how I'm trying to move and how it can best assist me. This can be used on something like a lifting task, where we need to lift something large or heavy together. And you can imagine this being used in factories, warehouses, or even in your home with a personal robot assistant. This hopefully makes it more similar to how you would lift an object with another person. So imagine you were lifting a large couch or something heavy in a factory. They would normally match how you're moving to keep the object level, but then you might nudge them a little higher or lower to get a better angle. And this is exactly what we can do now with the robot, just using your muscle signals. The robot can estimate how high I'm moving my arm, just using my natural motion, and then I can tense or relax my arm or make small gestures to command the robot non-verbally. The system uses my muscle signals as a way to communicate with the robot as we work together on physical tasks. And to do that, there's a number of algorithms and signal processing techniques that we do on the muscle signals to be able to estimate how I'm moving my arm and when I'm making gestures or other nonverbal commands. So we first read the muscle signals using sensors called EMG sensors, and these are basically tiny antennas that are stuck to my skin. And as I tense or relax my arm, it will pick up on the electrical signals that are running through my muscle. These signals can be seen here in the yellow, where as I tense my arm, the signals become larger. But EMG signals in general can be pretty noisy and hard to interpret. So we first have to process these signals. And we do this by filtering them, detecting their overall muscle activity, and then running those through algorithms that estimate how my arm is moving. And the output of those algorithms can be seen down here, where as I lift my arm, it estimates that my arm is moving up. As I relax and move down, the robot would also move down. Once we make those estimations, we can send those commands to the robot, and the robot can move to assist me while lifting the object. In addition to estimating my continuous motion, I can also send nonverbal commands to the robot. And I can do this using small gestures or tensing or relaxing my arm. To make gestures, I have EMG sensors around my forearm using a wireless sensor. And as I gesture to the left or the right, the inside of my forearm and the outside of my forearm, shown in yellow and blue here, have increasing muscle activity. And these muscle activities are sent to a neural network that classifies whether I'm making a left gesture, a right gesture, or no gesture at all. So in addition to using my biceps signal to estimate how my arm is moving up and down, we can also make small up or down gestures. And these are classified by a neural network by looking at both my biceps and my tricep signal. If I make a small gesture up or down, then the robot can move in that direction. And this allows me finer control over how the robot is moving, and also allows the robot to stay at a position that's very different from the position of my arm. So instead of always keeping the object level, I may want the object at a specific angle. And making gestures is an easier way to tell the robot that I want it much higher or lower than where my arm currently is. So I can, for example, gesture to the left or right to tell the robot where I want it to grip the object. And a neural network processes the muscle signals from my forearm to determine when I'm making the gestures. Once the robot is in a good spot, we can start lifting the object together. So once I grasp the object, the robot also engages, and then estimates how I'm moving my arm up and down. It also matches my stiffness. So if I'm just holding my arm loosely, the robot also remains compliant, and we can adjust the object. If I lift higher and stiffen my arm, the robot will become more rigid so that we can pull the object taut. Once I relax, the robot will also disengage from the object.